Swayam Prabha. Digital India. Educated India.
Welcome the next speaker. The next presentation is a contribution from IIT Delhi. The presenter is going to be Prof. Rina Sharma on this, and the title is Multi-Objective Optimization of Hybrid Renewable Energy Systems in the Presence of Uncertainty.
Thank you, sir. Good morning to all of you. Now, I'm Rina Sharma from IIT Delhi. I'm here to present my topic. My topic is a multi-objective optimization of hybrid renewable energy system in the presence of uncertainty. So first of all, I started with the presentation outline. My outline is as follows. First, I started with the introductions, motivations, challenges, target 1 and target 2. Basically, my problem is divided into two parts, where we can first solve the first target 1, and then we can go to the target 2. And the last section is the future scope of work. So let's start at the introductions of renewable energy resources. Renewable energy is the energy that we can obtain in a sustainable way and from natural resources such as sun, wind, and water. As we all know that they do not generate a greenhouse gas emissions, and the resources from which they are come are considered as inexhaustible because they are periodically renewed. But the question is around that from where we can get the motivations to use of renewable energy resources. As we can see that from so many years, the greenhouse gas emissions by economic sectors like industry, land use, building, transports, and other energies are found that the direct emission is about 75% of the total, and the emissions from electricity and heat production used by this sector is 25% of the totals. But as we can think about the source-wise consumptions of an energy, so we can find that the coal is used maximum as compared to the crude, petroleum, hydro, natural gas, lignites. So the point is coming out that here by the using of fossil fuels and by the using of crude and petroleums, we lead to so many problems. Issues like that, the global warming issues, environmental issues, and issues related to the health. So one of the great example of is that the Badarpur power plant in Delhi. The plant is shut down because of the largest emissions from the plants. So to overcome the issues of renewable energy resources, as we all know that the renewable energy resources are intermittent in nature. It means that they are dependent upon the weather conditions. So that's the single renewable energy resource is not able to complete the load demand. In that case, we need an HRES system, hybrid renewable energy system. HRES is a nexus of various renewable energy resources. It decreases the environmental pollutions, energy savings. It can also lead to help in socio-economic developments. It means develop employment opportunity in rural areas. It also abatement the global warmings. But the question is coming out here is again that the HRES is associated with so many challenges. Challenges like accurate estimations of real-time state variable, site dependency of renewable resources, configurations and sizings of hybrid system components, optimize the performance of energy systems, and optimize the local energy exchange for multi-HRES network. So to keep all these challenges in the mind, I just first started with the target 1. Target 1 is the accurate estimations of real-time state variable. As we know that during the demand side management or during the real-time trading of an HRES system, we find the accurate estimation of state variable. Here the state variable is related to the variable like current, voltage, and temperatures that are coming into equations of a solar fuel and electrolyzers. So to rectify the inconsistency of a measurement error in this subcomponent of an HRES systems, we move forward to the data reconciliations framework for dynamic operation of HRES systems. So let's come to the first proposed schematic of an HRES system that I consider in this work. I have renewable energy resources, wind turbines, solar PV cell. The power from the wind turbine and solar PV cell is passed to the electrolyzers, and here I'm using a chloralkali electrolyzers. From there we can use hydrogen. The sum of the hydrogen is storage, and the sum of hydrogen is passed to the fuel cell. And as we know that the fuel cell can convert the chemical energy into the electrical energy. And with the help of inverter, we can complete the load demand. Diesel generator, the power from the diesel generator is split into two parts, PD1 and PD2. PD1 is directly complete the load demand. In that case, where the solar, we have insufficient solar radiations, like in a morning, in the early mornings or in a night timing. And the PD2 is the power that can supply to the electrolyzers, and again, with the help of an electrolyzer, we can get in hydrogens. The power, we also have an external grid, and the power from the grid is split into two parts, PZ1 and PZ2, where the PZ1 is a power directly supplied to the load, and PZ2 is the power if we can need in case of insufficient supply of solar and wind. So, but these subcomponent like that wind, solar, electrolyzer, and fuel cell, these are the subcomponents. They have several equations like that. Solar, from the proposed framework, I just explained it. Solar photovoltaic cell, fuel cell, they contain algebraic equations, and for solving the algebraic equations, we need a steady state data reconciliations. For electrolyzers, we have a differential algebraic equations, and to solve it and to remove the measurement error, we need a state estimations technique like EKF, ensemble Carnot filter, extended Carnot filter, and regularized particle filter, and then after we can get reconciled results. Reconciled data is the current, voltage, and the temperatures. We can perform these data reconciliations for 3 operational scenarios like single rate, multi-rate, and sensor outage. So first we come on the state estimations techniques. How can I perform the data reconciliations from the all 3 subcomponents? So the first we have an initial state, X naught and P naught, these are the initial state. And with this initial state, we can go to the new state by predicting based on physical model and the previous model that we have had. So in that case, U is a control variable matrix, W is a predicted state noise matrix, and Q is a process noise covariance matrix that keep the state covariance matrix for beginning to small or going to 0. Then after we can calculate the Kalman gain. In Kalman gain we have a P, and R is a sensor noise and measurement covariance matrix, and from where we can get a state covariance update and the state update and the covariance update, and we can calculate the predicted the next update state of the systems. But the regular particle filter, the one of the best thing in state estimation technique is the regular particle filter. Why we use this RPF? Because in the rest of the estimation techniques like EKF, ENKF, we have a problem of degeneracy. So RPF is devised to overcome the issue of sample improvement, or we can say that the degeneracy. In RPF, the initial particle and prior particle generation steps are same as the mentioned in the EKF and ENKF, but the resampling steps is different here. So let's start it with the RPF, now how we can generate the new state. First, we have an initial particle generations. In that case, we first assume that the initial states of PDF functions that we have known and an initial particle based on the PDFs. Then from that, we can first calculate the prior particle generations, and on the basis of prior particle generation, we can get an next states. Then we can calculate the relative likelihoods of each particles and normalize the value of this relative likelihood. In that way, we can generate posterior particles by removing a relative likelihood QI in systematic samplings. Then after that, we can perform the 2 point. First is that to generate a random number R, which is uniformly distributed between 0 to 1, and then collect the relative likelihood into sum by cost at 1 at a time, and the sum is greater than R with some probabilities. Now we have a posterior particle with the distributions. So up to that part, we can get comparing the 3 estimator like EKF, ENKF, and RPF. So we just find that the estimation accuracy and computational time. So RPF estimations is better than the ENKF and EKF, and computational time is just reverse of the estimations accuracy. So from here, we can conclude that we can use an RPF, regularized particle filter, for removing the measurement error in the subcomponents of Acharya systems. This is the results of an RMSE value of a reconciliations from the single rate sampling for electrolyzers. In that case, we just found that at the top of the bottoms of the table, like the DAE RPF, we have a number of particles of 50. In that case, the estimations in temperature and estimations in current is fine, as is better than the ENKF and EKF, but the computational time is more than the ENKF and EKF. So from that, the first target one, what we can conclude that the combined linear data reconciliations and dynamic state estimation technique for different scenarios as proposed in this work. In this case, electrolyzer case, we will models the DA equations, and the 3 different techniques are used, DA, EKF, ENKF, and RPF for dynamic state estimations. We just find that from the result that the simulations results of a solar fuel cell despite the significant improvement in the real-time state variable estimations, and the using of an RPF is the one of the best thing is that the RMSE value we can obtain from the RPF is improved by 75% from DAE-KF and by 50% from DAE-NKF, and respectively with a fractional increment in the computational times. So let's first I just remove the measurement error by using the estimation techniques. Let's we move to the multi-objective dynamic optimization of HRA systems, or we can say that the state estimation aided optimizations. Now we have now motivations of a multi-objective dynamic optimization of HRA system is as follows. We have a real-time optimal energy flow for each subcomponent of HRAs. Because as we can go through the literature, we just find that the majorly work are done on the minimize the system cost and maximize the system reliability. But for the process of a dynamic operations is not held yet. So that's why we just move to the problem formulations involve challenges such as a variable with a nonlinear dynamics, require obtaining the optimal trajectory of a control variable in a real time in the presence of randomness. This study presents a methodology to handling all three objectives together by using a genetic algorithm for the optimizations and get the real-time optimal energy profiles for each subcomponent of HRAs. Now, first we just started with the genetic algorithm because we use an optimizations algorithm as a genetic algorithm. As we all know that the genetic algorithms are search-based algorithm based on the concepts of the natural selections or the theory of a Darwin that the survival of the fittest. So genetic are the subset of a much larger branch of an evolutionary computations, and it is used to solve the multi-objective optimizations problems. So here we have three objectives. First objective, let me start with the minimizing the cost, operating cost of systems, where we have a cost of grid into power of the grid, cost of fuel into fuel consumptions, and a cost of hydrogens, and multiply the hydrogen consumptions. Second objective is formulate as the proportions of a non-renewable energy resources, or we can say that minimize the proportions of non-renewable energy resources. Third objective is minimize the pollutant emissions due to the fuel combustions, because as I told in the previous slide, we have used diesel generators. So basically there's the emissions from the diesel generators. So how we reduce these emissions from the diesel generators? So third objective is to minimize the fuel emissions from the diesel generator. These are the constraints that are following. So here are optimizations. I just consider the three strategies. First strategy is our optimizations by analyzing the 24-hour ahead or day predictions. Case 2 is optimizations by penalizing the past history of data or 1 hour ahead predictions. And case 3 is optimization by penalizing 1 hour ahead predictions. This is our three cases that are considered in optimizations to solve the HRAs. So now come on the point of solution strategies. What the flowchart of a proposed algorithm that I considered here is a genetic algorithm. Now how the genetic algorithm used with an HRAs and calculate the three objectives. Firstly, the input used for this program is that the wind speed, solar radiations, number of wind turbine, number of solar panels, and the load profiles. So in that case, firstly, we initialize the populations by calculating the power from solar, wind, and with the help of solar wind speed, solar radiations, and wind speeds. After initialization, the decisions variable, we can pass it to the HRS simulations for calculating the value of all three objectives. Then after calculating the value of all the objectives, the ranking crossover mutations are performed or modified to calculate, to generate the off-screen solutions. This offspring solutions can combine with the parental solutions and can, with the help of a non-dominant sorting and crowding distance, it able to come. It find the elite. This elite can consider as an initialization solutions for the next generations. And this process is to take place until when we have generations less than or equal to the maximum generations. When we have this point, then we can stop it and we can get a parietal optimal results. And the question is coming out, we have so many parietal optimal results, and how we can get best results from there. So for that, we just go to calculate the operating point. There are several methods to calculating the operating point, but here we just normally use to weighing the all three objectives equally to normalize these values, and then we can find the final optimal solutions. So the analysis, basically this analysis and work is performed for the areas of Vadodara, Gujarat. Here the simulations time is 24 hours, and the problem is solved by genetic algorithms. In that case, there are some parameter specifications for the subsystem are as follows. So in that case, what we can find it? We find that the first case, the optimization by penalizing the 24-hour ahead or day predictions. We just find that the figure number A. Figure number A show that the Pareto optimal front for 24th time step for case 1. This is an operating point. There's a blue point that was an operating point shown by a blue color circle. Figure B is show that the locus of an operating point for time steps from 1 to 24. And the figure show that the predicting the Prabha trajectory for the 25th to 48th time step, we can say that the next 24 hours ahead for all HRS components. So the comparison, if we can, the question is coming out that how we can compare that our results are coming that are better than the another algorithm, or how we can validate these results. So to validate the multi-objective results that we can obtain from the ZS analytic algorithms, we can compare it with the single objective interior point method. We just find that in case of a single objective, we can get a value of one of the objective is best, but the rest of two objective values are worst. So in that case, what we can do it, we can just find that the multi-objective genetic algorithm, we get a value of all three objectives is minimized as compared to the single objectives solvers. Let me come on the point, as we can know that the solar radiation solar radiation is minimum in a day, in a morning day and the night hours. But in the afternoon, that was at a high peak. So in that case, what we can happen? In that case, if we have an excess of an energy, then we can sell it to the grid. So sometime in a early morning and a night durations, we can gotten a power from the grid if we didn't have enough solar and wind speeds. But in the afternoon timing, what we can do it, we can sell some power to the grid because we have an access of solar radiations. So if we can analysis of a buy and sale of energy between grid and HRS for the single and multi-objective, we just find that in the day hour we have a sufficient solar radiations and a wind speed, so that's why we can sell some power to the grid. Energy exchange analysis for the day-night basis from the single objective and multi-objective optimizations for the case 1, like a case 1 for 24-hour ahead predictions. In that case, what we can find it that the single objective and multi-objective, in the multi-objective during the 12 a.m. to 6 a.m. and 5 p.m. to 12 a.m., we just find that we just buy more energy from the more energy from the grid. But in case of 6 a.m. to 5 p.m., we just sell the more power to the grid. So what was the conclusion is coming out by using a multi-objective, by using a genetic algorithm in case of an HRS systems, we just find that the case strategy 1, it means that the 24-hour predictions can find to yield the best optimal solutions with 8.7% and 10.7% lower value of power brought from the grid, and 19% and 22% of higher power sold to the grid compared to the case 2 and case 3 respectively. Also, the results obtained using a multi-objective optimizations over the entire horizons are found to be more balanced compared to those obtaining using single objective optimizations. So if we just come to the 1 point, as I show that the challenges. So in that the challenges, we have a target 1 and target 2. First target is the accurate estimations of a real-time state variable that we can done. And the second thing is that the optimal sizing and configurations of an HRS systems that we can obtain after getting the genetic algorithm in HRS systems. So the future scope is the work is that we can, even in order to arrange and control and optimize the work, our future focus is toward application of a scheduling. If we can do it to transport the energy from one place to another place. And the second thing is expanded, there's some issues of sustainability is also coming into the picture. So extended my work in the field of sustainability assessment of power generations or green connected HRS and agrovoltaic systems. So thank you so much.
Thank you, Rina, for that very wonderful presentation. We can take a question.
Hi, great presentation, Rina. A few questions. First of all, do you have any idea about what's going to be the distribution of the different components of your hybrid energy system, and what's going to be the frequency of the, major dynamics in the power? That's one. This is going to be very helpful in once we have, hybrid systems operating. It's very useful to monitor and operate. You showed some, you found that looking at a 24-hour history, you were able to get a good conclusion on what's going to be the optimal
Yeah.
operating. Uh, have you tried looking at maybe how the seasonal variations are going to affect
Okay.
that?
Yeah, yeah. Thank you. Actually, the first thing is about the hourly study, as you mentioned that as we know that the solar and wind, these are the renewable resources that have an intermittence in nature, or we can say that they are depend on the weather conditions. So if we can consider the larger resolutions, so what we can happen, the accuracy to capture the true value is decreased if we can consider the larger resolutions, and the computational time is frequently increased. So why I'm consider the hourly resolution is here to make a trade-off between the computationals and the accuracies.
Yeah, I mean, it may become a bigger problem to solve, but just
Yeah,
looking
exactly.
at
We can also do it the seasonal variation, or we can say that it can be for the 1 year. In 1 year, as India, we have some different seasons, so we can also do it for the seasonal variation.
Okay, so you use some filters for this before the state estimation, right? So have you used some simulated data? Did you have models for each of the components for
Yeah.
which?
Yeah, I have a model of in each of the components, like solar and wind. We have components of in each.
And then you.
Then we can, with the help of that, where we can just proceed to the state estimation start next.
Okay, thank you.
Yeah, thank you.
Yeah, thank you for your presentation. I just have a question about the design of the system. So you define the size of the equipments. So can you comment about the differences between the multi-objective optimization approach and with uncertainties and the one that you obtain with the single objective approach?
Okay, like the sir, as I mentioned that the interior
You
point
buy
meant a single
different
point,
things, right?
single
So,
objective and multi-objectives.
yeah.
Basically, first I just clear that I just use a single objective is to validate the multi-objectives problem, because as we know that the genetic algorithm is a very computationally expensive algorithms, and we cannot say that if I'm using a genetic algorithm, so that's why very high comments that why you use a genetic algorithm, because it's a very complex algorithms. So to validate this, we just use an interior point methods, and with uncertainty and without uncertainties, what happened in that case, if we can use in a single renewable energy resource like solar. So in case of solar, what was the uncertainty? Uncertainty is that the presence of a solar in a day and night times. That was the uncertainty related to the weather conditions. Uncertainty is related to the site positions. And the second uncertainty is related to the diesel generator, like the emissions controls. So without uncertainty, if we can consider that, if we didn't consider the fluctuations in the solar radiations, like we can consider the one place. So the results is coming out like that normal. If we can validate these results by considering the uncertainty, then we can find that there's a big difference between the results by multi-objective GA algorithms. That I'm sure that the single objective in that way didn't have any filter or all these things. And by using a multi-GA algorithm, I just first state estimate, and then after estimate the state, I just proceed to the optimizations. So that was an state estimation added optimizations.
Okay, so you do not have comparisons, because what is important is the investment, right? Because you are dealing with the past, in fact, in your approach. So once you have the investment, then you will have to use the model for making a predictive approach. And I was just interested to know if you decide different sizes of equipments, if you take into account the uncertainty or not.
Yeah, so sir, can I say the one thing, sir? Actually, it's also depend upon the size of the component. It's depend upon the locations where you can use renewable energy resources. Like I just considered the Vadodara, the total maximum load is about 160 kilowatt hour. So here, I just do this study for the Vadodara place in Gujarat. If I consider another different place, we have different number of solar panels and different number of wind turbines, and on the basis of that, we can just find the optimal sizing. So that's why depend upon the locations, as I told. Thank you, sir.
Thanks. Let's give a round of applause again for Rina.
Thank you, sir. Thank you, sir.
Yes. Thank you, everyone, for making time to this session. This brings us to the end of the session. I think this is now the tea time. Thank you very much again for all your contribution. Thank you.